Okay, guys, we're going to have a series of short videos on statistical testing, and we'll start with hypothesis testing. So, as you know, it can be applied in 6 steps for the process, purpose of learning the process. It's best to use all the steps each time. So, number 1 is stating the research question, whether it's to do with comparing means or proportions or relationships among variables. State the hypotheses specifically, and we know that we do this in a particular format, the null hypothesis and the alternative hypothesis. Determine the statistical test to be used, and we'll talk about a variety of those. Determine the significance level, where we know we can assume the standard value of 0.05 alpha equal 0.05. This is the probability of a type 1 error. Right? And that has particular meaning in this context, which we'll review. Calculate the test statistics and then compare it to critical values that are defined by the test distribution. And then come to a conclusion about the null hypothesis. And there's always 3 parts of this. Do you fail to reject or reject the null? What do the numbers tell you given that? And then what's the managerial conclusion? Because again, that's this research question up here, it has some managerial dimension to it. We're only doing these statistical tests for a particular reason. In our journey here, we're going to illustrate hypothesis testing with 3 different types of comparisons of means. One is take a mean from a sample and compare it to some population standard or some global standard, usually to see if you match that population. Independent samples t-test is comparing 2 groups within a sample. And paired samples t-test is where everybody in the sample answers 2 different questions, and you compare the means of those 2 questions. Let's say, right? We've got 2 contexts for looking at this. One is a coffee example, which we're gonna plow through here momentarily, and then on the 4th video we're going to look at applications within SPSS using the survey on the spot data for the restaurant finale. Okay, and then in the application assignment, these are the corresponding questions. But let's jump right into the one mean test. Okay, the one mean test will be our little label for this. First, we got to calculate a mean to do this. So just a little practice on this was assuming that this is weekly retail coffee spending from a sample of 5 people. If you add up all the numbers, you get 9762. If you divide that by the number of observation, you get a mean of 1952. So on average, these 5 people spend $19.52 on coffee each week. The difference from the mean and that mean difference squared have very important implications for other summary statistics here. So if we take this first person's weekly spending, 2742 minus 1952, we get 790. If we square that, we get 6235. And if we do that with each other observation, you'll see we can sum up those squared differences. And those squared differences are important in helping us capture another index which we call variance, and then subsequently standard deviation. So the variance is taking all those squared differences, right? The sum of those squared differences is this number here, and divided by n minus 1, and it gives us the variance. The variance is a number which in itself, it doesn't look like it means much, but it does mean something when it comes to comparing across samples of the same, on the same variables, and as well as being interpreted into other summary statistics. The standard deviation is simply the square root of S squared. And in our case, it's $16.55. So these are simply metrics that capture how much range, how much variance is captured in the sample across these 5 different people. So to do this test, let's find a number here, and we just want to ask the question essentially: do we have a sample that seems to be similar to this population? Now, keep in mind that all statistical testing centers around a distribution that we assume represents the null population. So, or the null where the population is accurately captured by this $21.32 figure. In other words, there's a 0 difference. Another way to look at this: there's a 0 difference between our sample and the population. Essentially, if this is a null distribution, right, and this is what the t-test looks like, or z-test, we're going to put boundaries on it, because this is like the null world here, or nullville, or whatever we want to think about it. This is a place where all the samples you pull out are close enough to 2135 that we say, well, they're similar enough they fit in this population. But we got to put some limits on the population, right? If this is the full distribution, what we're saying, the limits we're going to put on is our 0.025. We're going to split that alpha into 0.025 and 0.025. And what that 0.025 refers to is the area under the curve here, right? What this means is that you might get an observation that fits out here, and we're going to say, nah, reject it. It's not part of the null population. When in fact it could be. There's a 2.5% chance out here, and another 2.5% chance out here that it's actually in the null population, right? So we'd be rejecting the null when it was actually true, right? We're willing to put a 5% chance on that, right? And that's why we have 2.5% in each tail. And that's really the judgment here. These are the boundaries of the world of null here. And we're going to say anything inside these boundaries, anything that fits in here along this continuum, is in the world of null, and we're not going to reject the null hypothesis, right? So our research question, sorry about that, I just covered that whole thing up. Does our samples bend at a rate that's the same as or different than the population average? And it's really a question, does it look like it came from the full population? For our sake here, we're just going to use a sample of 50, use the same numbers. So here are the numbers that we just calculated, right? Now, here's the thing, this is a very general point here. Every statistical test involves some comparison in the numerator and then uncertainty in the denominator, and it ends up being an index. So basically the question is the difference you get here divided by some measure of uncertainty, is it small or large relative to this population, right? Is it small enough to be considered in the null population? Uncertainty comes into play or is implemented, represented by variance in standard deviation, or what's called the standard error of the mean, which is ultimately the index we use here. The larger the uncertainty, the more difficult time you're going to have to reject the null hypothesis. More on that later. So here's our research questions. First of 6 steps. Is our sample mean $19.52 significantly different from the population figure of 2132? So we're going to say we're comparing our sample to this null population, this null representation where $21.32 is the mean. The alternative hypothesis is that the mean is different than 2132. One sample t-test, show you in a second, alpha equal 0.05. The test statistic looks like this. Just a classic t-test with, here's your comparison. The observed mean, 1952, minus some standard, which is the population figure, 2132. Divided by the standard error of the mean, and you guys have seen that figure before. It's kind of the estimate of the population standard deviation, and what's one way to think about it. In our case here, we have an observed, what I just showed you. 2132 is the standard, and the standard error is 1655 divided by the square root of 50, which gives us 234. When we calculate the t observed, that's how we're going to refer to the calculation from the sample, we get a standard error of the mean of minus, or no, I'm sorry, we get the t statistic of minus 0.77. We're going to make use of that now to make our comparison. Here's our null population figure. So this is 21, now I can't remember, 35. And we get a test statistic of minus 0.77. So it's obviously lower than the 2135, but it is clearly within the bounds of the city limits of this world of null here, right? So it is clearly within the large part of the distribution. It is not in an area where we would reject. So we're going to fail to reject the null. What do the numbers mean? That's A. B, what do the numbers mean? Well, the statement is our sample consumes coffee at about the same rate as the national average. Even though it's lower numerically, about $1.80 lower, what we're saying is that it's close enough with the size of the sample and the variance. It's close enough to be able to say, well, it looks like there's the similarity here. So some evidence that this sample looks like it's representative of the population. Okay, all one sample t-tests kind of follow this format. You may be comparing different things. You may be comparing average consumption to population. You may be comparing attitude scores to certain extremes of the scale. A variety of things that you might do, but that's the one sample, one mean t-test. More on the next test on the next video.